bit excited to introduce Geraud. We've had a lot of interesting talks in the past, and he was an ex-lab mate at my old university. But more than that, Geraud's going to be speaking about logical composition and how it can help with generalization and reinforcement learning. Geraud is an IBM PhD fellow and a PhD student in computer science at the University of Witwatersrand. He's been fascinated with the immense potential for creating intelligent systems. I think some of the work he'll speak about will hopefully be steps towards this. And he feels like these intelligent systems are the pinnacle of what is AGI. So maybe we can ask him some interesting questions on that a bit later. Geraud's main research interests lie in reinforcement learning, since he believes it's the subfield of machine learning with the most potential to achieve AGI. In particular, his work is focused on principal approaches for efficient compositional generalization in RL agents. So I think it'll be quite relevant to a lot of people in the group, and I'm quite excited for his talk. So I'm going to hand over to Geraud.
Awesome. Thanks for the really nice introduction, Caleb. Yeah, and it's been a while. Yeah, and also thanks you guys for kind of like inviting me for this presentation. It's really an honor and privilege to kind of like present to you guys. And hopefully some of you guys find this work interesting. I'm definitely really passionate about it. So hopefully the slides are not too trash, and hopefully they at least convey the general idea well enough. And as Caleb mentioned, I'll be presenting on logical composition and how I kind of like thinking about it in terms of helping us get more general agents in reinforcement learning. I'm sure. So Caleb and Samuel kind of told me that a lot of you guys are kind of like interested in reinforcement learning and different aspects of it, like generalization, reinforcement learning, lifelong RL, and all of that. And so I'm sure then that many of you have kind of like heard about generalization or lifelong RL from different perspectives, or from different angles. There's like certainly multiple ways of trying to tackle this like massive problem. And the particular angle from which I kind of look at the problem is like I kind of want to hopefully reach a point where we can have agents which are general, not just by kind of trusting functional approximators, kind of generalize over the space that we are interested in, but kind of having some degree of provable generalization, right? And one approach towards this, or one promising approach towards this, is composition. So cool, so that's kind of like, I guess, the preface. So one thing that we are all interested in is like ultimately having multi-purpose robots, right, that can kind of solve a variety of tasks in the world, right? And to kind of have this, one of the key aspects that it needs to be flexible, right? Imagine that you have this domestic robot, I don't know, in your lab, for example, and maybe you want it to, I don't know, go and fetch some cup of coffee, or your favorite type of cup of coffee, be it like sugar or milk, or no sugar or no milk, like going the classical way, or some other type of like lunch or anything like that. Then, and different people will have different things that they kind of want the robot to do, right? So it needs to be flexible enough to be able to do all of these things. It needs to kind of like be general enough to be able to do these things without having to do additional learning, right? And if you need to do additional learning, then it needs to be sample efficient enough to be able to do that learning as fast as possible. So the kind of two key aspects I kind of really want to put a big emphasis on like for this kind of whole approach towards solving this problem is the idea that we want ways of making robots flexible, or making our RL agents flexible. Doesn't have to be physical robots. And we also want to put some guarantees into what our agents are able to do, be it in terms of sample efficiency or be it in terms of like generalizability. So if you kind of think of human beings, I think this is like one of the inspirations that most of us kind of take our inspiration from. Look at how general human beings are, right? If you kind of look at the human being from the moment where they're babies to as they grow up to like adolescence to adulthood, you kind of see that they are able to kind of leverage the various skills they learn in their earlier ages of like of development. And you're kind of able to kind of like reuse those skills as they grow up and kind of like be able to generalize beyond the skills or the tasks that they learn to solve in kind of like prior points during their life. So they have this general idea of flexibility and generalizability and sample efficiency, right? But if you kind of look at current RL, it is really trash at all of these aspects, right? Current RL is kind of like famously known to need like millions or billions of episodes or samples to kind of like learn a single skill, right? A single skill. And then for every single new task that you want it to learn, you have to again spend all of this compute. So that is not ideal, right? We want to hopefully be able to solve multiple tasks, and we kind of don't want to have to learn every one of them independently, right, from scratch. So that's kind of like the problem. So the general idea is that we want to be able to kind of transfer knowledge between tasks, right? Reuse some of that knowledge that we have spent time and effort learning in prior tasks, reuse that knowledge in new tasks. So what do we want for this work, right? We kind of like ask this question: if we are presented with a new task, can we kind of like figure out if that task is expressible in terms of the ones we have already learned, right? If yes, then if this is expressible in terms of the ones we have already learned, then ideally we should be able to solve it zero shot, right? We should be able to compose the knowledge learned to solve the new task zero shot. If not, then we should at least be able to kind of like use what we have learned and our estimate of how it is related to what we want to solve to kind of like at least do some future learning, right? Not have to learn the new task from scratch. So those are kind of like two of the core things we're interested in here. And if you're able to do both of those things, then what does that say about generalization in lifelong RL, right? Can we put some bounds on the number of tasks we need to learn, given that the tasks are sampled, let's say, from some unknown, potentially non-stationary distribution? So that is kind of like what we're interested in answering here. And the kind of like, so when I speak of a task expressible in terms of previous ones, at least for this work, we kind of constrain ourselves to logical compositions, right? If a task, for example, let's say for example, for a new task, the agent needs to, let's say, do X and do Y simultaneously, or do X until some condition is met, and then do Y, right? Something like that. Of course, like the space of tasks of interest are larger than this, but at the very least, this is something that we would expect the agent to be able to do if he has already learned the kind of like necessary subcomponents of this task. And so we kind of like want to be able to do things like this without having to relearn every single such task. And also we want the kind of behaviors we get from our agents to kind of like be theoretically verifiable, right? We want to put some guarantees onto those behaviors or onto the generalization abilities that we get. So that's kind of like the general idea. Now, I'm sure all of you have seen these pictures to death by this point, but let me just kind of like give a brief overview of the RL loop. So you have your agent here, which is our cute robot, and that agent takes actions in the environment represented by the cute Earth, and then the environment returns some observation and some reward, some scalar signal to the agent, and given that new observation, the agent takes an action and so on, right? And ultimately, your agent is trying to learn a policy. Can you guys actually see my mouse as I'm moving it?
Yes. Yeah, we can.
Awesome. For some reason, is a pointer. Okay, this is maybe better. Cool. So your agent is trying to learn a policy that basically says for each state, what is the action it should take, right? And to kind of do that, a useful knowledge representation is something called the value function, which basically says what is the expected cumulative reward if you execute that policy in the environment, right? And ultimately, what the agent is trying to learn is a policy that maximizes this value function, right? A policy such that when the agent executes that policy in the environment, is going to get the highest expected rewards possible, cumulative rewards. So PyStar basically represents the solution to a single task. Cool. So now let's speak about this notion of compound tasks, right? About tasks being expressible in terms of other tasks. Let's formalize what we mean by that. So let's say you have two task MDPs, A and B. Right? MDPs is, as many of you will be familiar with, is kind of like the structure we use to kind of like represent tasks in reinforcement learning. So you have two MDPs, A and B, and they both have rewards, let's say A and B. Then what we kind of like mean by, let's say, A union B. So here, for example, A here, I'm basically kind of using a truth table to kind of like represent, let's say, for a given state action pair, the reward for A is 0 or is 1, and similarly for B. Right? For all of those combination of rewards for A and B, what is their union? Well, their union is going to be, let's say, 0 if both A and B are 0, and 1 if either one is 1. Similarly for intersection, similarly for the not of A. So that's kind of like what we would mean by the composition of A and B. So those are going to be, in the case where the rewards are 0 and 1, those are going to be the rewards of the composed tasks. All right, and formally, what does this mean? So if you are kind of saying A or B, then basically the reward function for that new composite task is just going to be the max over the reward function of A and B, right? The intersection is just going to be the mean over their reward functions, and the negation is just going to be a constant minus the reward function. So that's what we formally mean by composing MTPs. And kind of one assumption that we make here for all of this to kind of like make sense is that the rewards must have the so the task, the MTPs A and B must have the same rewards everywhere except at the goal states. That kind of like pretty much translates to we are interested in goal-reaching tasks for this setting. Cool. So that is kind of the setting and what we mean by composing tasks, and that will kind of like enable us to kind of like formalize how to decompose new tasks into their potential subcomponents later on. So given that, the next question of interest is like, what type of knowledge representation do we need to be able to learn to solve any such composition of tasks if we already know the subcomponents? So one thing that I kind of introduced in prior work, this was back in Europe 2020, was that if we are really interested in solving new tasks, zero shot, or be able to transfer knowledge from current tasks to new tasks, then we need to learn a bit more than what we usually learn in reinforcement learning. Right? It's a single policy PyStar is not enough to be able to maximally reuse knowledge learned from prior tasks. And so I kind of introduced this idea of an extended family of word value functions, and I kind of like calling that word value function because I kind of capture the type of knowledge representation I am thinking of. So while solving a single task, we should learn about other tasks that kind of may need to be solved in the future. And that's kind of like the general idea. So how do we do that? Well, the way I kind of thought of doing this is using a very simple extension to your traditional reward functions and value functions without adding any additional assumption over what you expect from your MTP. So the way I do that is say the agent is going to define an extended reward for itself. You can imagine that's like an internal reward function of the agent that is goal directed. Right? It's going to be such that if the agent reaches a goal, which is defined as terminal state, if the agent reaches a goal that is different from the goal it was trying to reach, then it's going to give itself a large penalty to come say, I have failed to reaching the goal I was interested in reaching. Otherwise, it's just going to receive the regular reward for the MTP. So that's how we modify the reward function. And next, we modify the policy to be goal-based too. So now this is going to be the policy for this reward function that has been defined here. And we're also going to modify the value function to be goal-based by just saying that it's going to be defined based on this internal goal reward function. So that's how we are going to modify the knowledge that an agent learns in reinforcement learning, such that it's going to be useful for downstream transfer and composition. Okay, I hope that makes sense. Also, by the way, if anyone has any question as I'm kind of like going through all of this, just feel free to kind of raise your hands. Cool. So the penalty again is given. The agent gives that to itself if it reaches unintended close. Yeah.
Is it fun to ask a question?
Oh yeah.
Okay, cool. So why would I guess conditioning these reward function policies value function on this goal allow you to learn about other tasks? I'm not sure if you're going to explain that.
Yeah, so I'm going to show an example in the next slide and then kind of like explain why that works.
Okay, cool.
Cool. Cool. Although I'm not going to, hopefully this explanation is going to make sufficient sense, and because I'm not necessarily going to go into too much details there. But essentially, so this is an example, right? So let's say the agent, is in this environment with different objects, with different shapes and colors, and it needs to learn how to collect blue objects. So basically, the rewards it gets is, let's say, minus 0.1 for each step, and then let's say a reward of 2 when he picks up a blue object, right? And so if you were going to kind of like learn a regular value function on policy, then at each stage here, all you will really know how to do is how to reach the closest object, right? And what is the value of doing that. But if you learn the word value function, again, this is without adding any additional assumption, any additional knowledge required for the agent to achieve this, just using the regular MDP setting and just doing this extension over the reward function of the MDP, the agent is able to learn this word value function, which basically contains the value function for achieving every single goal in the environment. And not only that, it also kind of like represents the value of achieving those goals in the current task. So you can see, for example, that it says that if you're trying to achieve purple circles or beige square, all of those have low values, but blue objects have high value in this environment. So it echoes both the value of achieving them and the policy for achieving them in the current task. And okay, so then the question is like, why, or like, how does this simple modification lead to this result? I think like the kind of like simplest answer to that is, imagine this agent is trying to reach, let's say, the beige square, right? And it discovered the beige square goal when it was randomly acting in the environment and stumbled upon that goal. So that is how it discovers the set of goals in the environment. So now let's say that it has conditioned its value function on beige square and it is trying to reach it, but because of random exploration, right, it maybe goes to a blue circle instead of a beige square. Then it's going to give itself a large penalty for reaching that blue circle. As you can see, basically reaching any goal in this environment except for the beige square is going to give itself a large penalty. So those are not optimal objects to reach in the environment. And so the optimal thing for the agent to do is going to be to go and reach this beige square if that is the goal it is trying to reach. And that is irrespective of the current task. Or the current task is collect blue objects, it's not collect beige squares. But for this word value function, it's still going to learn how to reach beige squares. And equally, it's going to learn how to reach purple squares, blue squares, and all of these other objects, irrespective of the current task. And then once it has learned this knowledge representation, one natural question is, okay, it has learned all of this, but the task that it was asked to solve is collect blue objects. So how do you actually get that policy from this knowledge representation? The way to do that turns out to be straightforward. You just need to maximize over goals. So for each state, you just maximize over goals, and then you recover the regular value function, which you can then use to maximize over actions and then get the policy to actually solve the given task. So that is pretty much the whole idea, is that we are not going to learn a regular value function. That is not enough for downstream generalization. we kind of like present arguments for that in the NeurIPS paper. But so the idea is that we are going to instead learn word value functions. And then when we want to solve a given task, we're just going to maximize over goals to solve that task. So we can do that for, let's say, blue objects. We can do that for, let's say, square objects. We have these two word value functions. We are able to solve the given task. And now we are able to combine these two word value functions to solve any logical combination over them. For example, let's say that, let me just go off, like, let's check something quickly here. Okay, let me go back. Okay, so you're able to solve any logical combination over them, all right? So how do we kind of like do this? So let's say again that you have your task A and B, your reward functions A and B. You have defined the compositions over their reward function, all right? So we know what A or B means in terms of the composed MDP. The way we are going to obtain their corresponding optimal policies without having to do additional learning is by applying the exact same operators over their corresponding word value functions. Right? So let's say that we now have learned the word value function for A and the word value function for B. Then, to obtain the word value function for A or B, just take a max over the individual word value functions. And this is a pointwise max. Similarly for the intersection and similarly for the negation, we are going to take a constant times minus the word value function. And as I mentioned earlier, if we do this, we get the word value function for the composed task. Then we can just maximize over goals to actually solve the task. So let's kind of like demonstrate that. So let's say, for example, now you need to solve blue intersection square. Then after taking the mean over the word value function for blue and the word value function for square, this is what we get. And essentially, the way you can think of what is happening here is that this was the word value function for blue and this was the word value function for square. For in both of these word value functions, the value function with respect to the blue square is high, right? And the word value function with respect to all of the other objects is not consistent in both tasks, right? So for example, a blue circle in the blue word value function is high, but a blue circle in the square value function is low. So when you take a pointwise mean across both of them, it has the effect of basically leaving the value function with respect to blue square high and the value function with respect to all of the other objects low. So that is kind of like how the composition is able to get the word value, by just taking the mean, is able to kind of get the word value function for intersection without further learning. And then you maximize over goals, you get the regular value function for the intersection. You can see how this is a blue square here, and the value function kind of like gets higher as you get closer to the blue square. And then you maximize over actions, and you're able to actually go and collect the blue square. And you can do this for any logical composition of blue and square without further learning. So this is their union. This is their negation, the negation of a square task. So you can see the agent going and picking up objects which are not square, even when it is like near a square object, right? It goes and picks up something that is not a square. And then we can, of course, do more complex compositions, right? Like exclusive or pick up an object that is blue or square, but not a blue square. So you can see the agent here is close to a blue square, but it doesn't go to it. Instead goes to a purple square, which is further away, right? So that is kind of the general idea. And so one thing I mentioned earlier is that we want these things to be provable, right? We want to put guarantees on this. Otherwise, how is it really different from just trusting a neural network to just be able to generalize over the space of compositions? So, and this is what we did in the NeurIPS paper. We kind of proved that for the union, intersection, and negation, we are able to recover the optimal policies zero shot by doing this composition approach I just illustrated. And so you can imagine, for example, that if you have task A is maybe this task here, requiring the agent to maybe go to the left rooms. Task B is requiring the agent to go to the top rooms. Then going to any of these top or left rooms, the intersection is going to be to go to this top left room. Negation of, let's say, the left room is going to be the right one, and the exclusive OR is going to be something like that. And for all of these compositions, we can get their corresponding reward function zero shot. So maybe let me illustrate that in this domain here. So this is like a Mujoko Ant domain. And unfortunately, the Microsoft PowerPoint online is trashed. So this is the only way the animations are going to show. Hopefully you guys can see the animation, even though it is. Yeah. So here, the agent has learned how to go to the left room, or whichever one is closest to it. And then, maybe zoom further. No, let me not jinx this presentation. Okay, so it has learned to go to the left rooms. Now, let's say it has also learned to go to the top rooms. So it has learned those two base skills. And now you can compose those two to go to the top or left rooms, whichever one is closest. You can go to the top and left rooms, right? So to the top left room. You can also do their exclusive OR. Go to the top or left room, but not the top left room. And it does all of this zero shot without further learning by just applying the computation operators I've shown earlier. Cool. So that kind of pretty much covers what do we mean by computation of tasks? How do we obtain the resulting skills without further learning, assuming you have learned the required base skills, right? What this kind of pretty much give our agent is this blessing of dimensionality, right? We are used to curse of dimensionality, but this is one example where dimensionality actually works in our favor. If the agent has learned how to solve k-based tasks, so it has k-based skills, then it is able to solve 2 to the k tasks, right? A super exponential explosion in the agent's abilities.
Geraud, sorry to interrupt. I think there's one hand up.
Oh, yeah.
Yeah, I had a question, Geraud. What is the state space you're using for the Mujoko experiments?
It is, let's see if I remember. So it is the kind of like the regular one for the Mujoko ant. So it is things like so the ant has like 4 joints. Was it 4? No, 8 joints. So it is kind of like the joint velocities and joint angles, and what else? The XY position of the ant, and yeah. So basically, it's a vector.
You do get the XY position of the ant as part of the state space.
Yes, although actually I don't remember if when I was doing this, I used a relative position where the ant was the center of the world, or if I used the absolute position, but basically it gets that.
Yeah, well, because like my question was basically I can see intuitively how this approach would work very well if your goals can be linearly, combination of goals can be linearly decomposed. I'm wondering, like there's another like setting for that's particularly studied in zero-shot generalization, where you assume that between your different tasks, you have some representation of your observation or state that will be generalizable for all tasks, but it may be a nonlinear function that gets you to that representation. So I'm thinking, for example, if you try to pick up an object and the object texture, friction, or shape may change, then you have this sort of you can sort of picture like the generalizable policy of would be like one that has first a representation function that maps basically every possible task into a space in which they are equivalently solved by the same policy. And yeah, so I'm wondering how does if you didn't have like this XY position already given in your state, could you still use this decomposition method?
So if we didn't have the XY position in the state, then we even wouldn't be able to learn a regular policy in this case. Otherwise, because the state would be Markov, right? The agent would know what its position is. And yeah, so if you're not able to learn values or policies, or if your MTP is not Markov, then this wouldn't work, and regular array wouldn't work. I guess maybe but that's a different kind of like situation from what you're describing, because in what you're describing, the agent will kind of like be basically generalizing over let's say features of the environment or features of the states that are kind of like say equivariant with respect to their policies, right? So like basically where the policy is going to be the same irrespective of those change in features. So maybe if the ants had like different colors or of their legs of the legs, or maybe there was a different coefficient of friction on the floor, or maybe there was a bit of noise in the XY position or things like that, then maybe you want your agent to still be able to execute the exact same policy or generalize its policy across all of those different changes in variations in the state, because ultimately that doesn't change what the optimal policy should be doing. So yeah, so as I was saying, I would say that is going to be like a different type of generalization than what I am kind of like looking at here. And for those type of generalizations, discover a different family of things that you'll be interested in, right? Like we mentioned, for example, kind of learning or like of assuming or learning this general, I maybe call it latent representation that is common across all of those variations in state observations, so that your policy is basically dependent on that latent representation and doesn't care about the distracting variables in the state observation. That could be like one way of doing that. And I guess you can combine all of these angles towards generalization, right? You can combine that with kind of like the type of generalization I'm looking at here. But yeah, I don't know if that answers this question. That answers the question, but I guess the long and short is that if you don't have XY positions here, then your environment is not even Markov in the first place, and you are not going to learn anything.
Yeah, I think you answered my question. Basically, like the way I understand it is that the compositional generalization setting you study is where you can linearly decompose or logically through logical operations you can get to the new task. And I guess I was still thinking like you would still see you will be able to represent the XY position in some way, so it will be Markovian, but you maybe like in one task you will have a different projection of XY. So maybe one is expressed in polar coordinate, the other one is expressed in some other coordinate system, and then you will need a nonlinear operation to be able to map back to a space in which X and Y can be recovered in a way that you can then linearly combine them to get compose basically tasks. But I can so now I understand that like in this setting you're assuming that this step has already been done, either through the formulation of the observation space or state space.
Exactly. And yeah, and in this case you are not focused on that step of generalization. You are more focused on the step where your reward function is decomposable logically.
Okay, thanks a lot.
That's cool. I mean, and I think that points out something that we have forgotten to mention, which is that ultimately, I think this is what we want, right? We want all of these aspects in which our agent should be able to generalize for agents to actually be able to generalize in those aspects. And we want that to become like, we want to do that in a way that is provable to some degree, instead of, again, hoping for a functional approximator to kind of like magically do all of that for us. So that is nice. Oh, and also I think the kind of ideas presented here, hopefully, at least I would be kind of like very interested in seeing this expanded in various other kind of like settings. For example, settings where the kind of decomposition of the of your kind of reward functions, not just logical, it's maybe like a nonlinear function or some other family of functions, and then be able to combine your existing scales to be able to solve those new tasks zero shot. I think that is kind of like the general thing I'm interested in, right? If a task is able to be represented in terms of past ones in some way, it could be in terms of state space, in terms of reward function, in terms of dynamics. We want the agent to, one, be able to identify that, and two, be able to actually do it, right? Do that generalization. I think that is at least one way I think we can hopefully get to more general agents in a satisfactory way, or in a way that you can actually put some guarantees on that. I'll just look at the time. Okay. Cool. So now that we're able to compose tasks and get their corresponding scales zero shot, let's see what that means in terms of the original problem I mentioned, which is how that kind of like helps us for lifelong array. So let's take this domain as an example. In this case, we have an environment with different objects with different shapes and colors, right? And here I've listed all of the goal objects in the environment. Now, let's say that the agent has learned how to pick up green objects, blue objects, yellow objects, and keys. And one thing that we are going to do here to be able to leverage logical composition in lifelong array is we are going to learn a representation of those tasks that the agent has learned. And that representation is going to be a binary representation, right? So we're going to learn that, for example, in the green task, the agent gets 0 rewards when you pick up like red keys. It gets 0 rewards when you pick up like red balls, but it gets maybe a reward of 1 when it picks up like green balls, right? And so on. So it learns a binary representation of the task. It does that for each task it has learned. Now, let's say that it's given a new task where it needs to pick up yellow keys. So in that new task, it is going to, and this approach I call it sub-goal. It basically represents sum of products in goal-oriented learning. So what it's going to do when it's given that new task is it's going to first learn the binary representation of the task. And again, this is in the regular array setting, right? So like it's exploring the environment in the model-free way. And then when it reaches like a goal object, it sees the reward it got, updates its estimate of the binary representation for the task in a supervised way. So it does that, it learns that binary representation, and then it can use a sum of products method, which I'm sure most of you are probably familiar with. If you have like a Boolean table and you have like a new vector, you can basically represent that new vector as a Boolean composition of the other vectors in the table by using the sum of products method. So if it does that, this is what it gets for its estimate of the new task in terms of the task it has learned. And so if you kind of look at what it has estimated here, it says that the new task requires the agent to not pick up green objects intersection, not pick up blue objects intersection, pick up yellow objects intersection, pick up keys, right? Which is exactly the task that the agent needs to solve, right? It needed to pick up yellow keys, and that is the only desirable goal in this task. So once it does that inference, it is going to use the computation approach I just explained earlier to get the corresponding scale, right, by applying the exact same expression over the word value functions that it has learned during those tasks. So now it has this composed scale, Q sub. Now, what it's going to do is it's going to check if the inferred Boolean expression is indeed representative of the task that it needs to solve right now. All right, so basically, it's going to evaluate this Boolean expression on these binary vectors it has learned and see if the resulting binary vector is the one for the current task. Right? In this case, if you do that by hand yourself, you're going to see that this Boolean expression indeed evaluates to the expression to the binary representation of the current task. And so it does that and say, oh yes, the current task is indeed representable in terms of the previous one. So I don't need to do any additional learning. All right, I can just use the skill I just obtained via zero-shot composition. And this basically reduces the array problem into an easier problem, which is supervised learning. All right, and I see that something very funny happened with the spellings here, but you can maybe put like a mask over your eyes and ignore that. Cool. So that is a case where the new task is representable in terms of past tasks. Now let's take the other case where the new task is not fully representable in terms of previously learned tasks. So let's say that in this case, the agent needs to pick up yellow boxes. Notice how it has not learned how to pick up boxes in the prior task. So we're going to apply the same approach. We're going to learn a binary representation of the current task. So you see in the binary representation, all of the goals are zeros and the yellow box is 1. We're going to apply the sum of products method to get a Boolean expression representing this current task. So that is that here. Let me go back to the pointer. And here, so you see again, not green intersection, not blue, intersection yellow, intersection not key. Right? So at least it has identified that the new task involves picking up yellow stuffs, but it hasn't learned about squares, so it doesn't know about squares, right? And so when it so again, it applies the same expression over the learn word value functions to get an estimate of the word value function for the new task. And then it evaluates this Boolean expression on these binary vectors and sees that it does not return the binary expression for the current task, right? And again, if you do that evaluation yourself, you're going to see that T is not equal to T prime. And so that is how it determines that, oh, this current task is not expressible in terms of the past tasks. And so in this case, it won't just disregard this composed value function because it is still useful, right? It has at least identified that yellow objects are desirable. That kind of cuts down a bit on the kind of exploration problem for the current task. So what it's going to do is it's going to learn a new word value function for the current task, but it's going to use the estimate of the word value function for the current task, Q sub, to speed up training. And once it does that, once it learns this new Q function, it's going to add that to its library of skills. All right, so after learning this, it's going to have green, blue, yellow, key, and blue box in its library. I'm not going to go into much detail in how you use this Q sub to speed up training, but basically I incorporate that into the exploratory behavior of the agent. And I'm going to show an example of what it looks like later on. Cool, so that is pretty much it, right? An agent is able to kind of like identify if a new task is expressible in terms of past ones. If it is, it's able to solve it zero shot. If it is not, it is able to at least speed up learning of the new task and then add the newly learned skill to its library of skills. So now let's take this very complicated task that involves, again, I have no idea what has happened with my labeling here, but I'm going to translate it for you. You can imagine maybe it is like some language in Star Wars or something. So the agent here needs to pick up red objects or blue objects or green objects. It needs to pick up red objects or blue objects or green. Let me repeat. It needs to pick up red or blue or green boxes or green or purple or yellow keys or blue balls. I think hopefully in your mind you have kind of like translated whatever typos I did there into what I just said. So for that task, if we apply the sub-goal approach that I mentioned, again, so this task is not fully expressible in terms of the pre-trained ones. If you look at the sample efficiency of DQN, we see that is what DQN, like how DQN gets better with time. The horizontal line here is a zero-shot performance of the estimated scale, of the estimated zero-shot scale of the agent. And the blue one here is the few-shot one. You can see that the estimated one already starts with a pretty high jumpstart performance, right? And the few-shot one starts from the exact same performance and then improves from there. Right? And if you look at the inferred behavior, it looks something like this, right? Which is very interesting. Right? One is that it is interpretable, right? You can read this and say, here's what the agent is thinking about with respect to what the current task is in terms of the previous ones it has learned, right? That is one thing. And the second thing is that so here I'm showing what it has learned in terms of the task representation, the binary task representation. Essentially, what you're seeing here is the binary representation as the episodes go, average over 4 runs. And as time goes, you see it converges towards the binary representation of the current task. And so it learns this binary representation, every episode updates it, uses that to infer the current task with respect to previously learned ones, and then uses that to either act in the environment zero-shot, or in this case, improve on the exploratory behavior to learn the new task faster. So that is the general idea and results. So the way it looks like is, so this is DQN only, not doing any transfer learning. We see that at episode 0, the earlier episodes acting randomly, right? It doesn't know anything. But if you look at the DQN plus sub-goal, DQN here is used as the offline array algorithm in this whole sub-goal approach. Then we see that even from the very first episode, it already has some goal-directed behaviors, right? Because it is starting from its inferred behavior. And then as it gets better and better estimate of the binary representation of the current task, that goal-directed behavior gets more and more directed towards the correct objects. And in the case where the expression fully represented the current task, then that goal-directed behavior is going to be optimal. Otherwise, it's going to slowly get better by the few-shot learning approach. Cool. So that is essentially the behavior of the agent. So what we did is we show that an agent like this, we can bound the number of tasks that it needs to learn throughout its lifetime, irrespective of the distribution over which the tasks are being sampled, right? That distribution also doesn't need to be stationary, right? It can be a non-stationary distribution. So you have the lower bound is going to be the log of the number of goals in the environment, and the upper bound is going to be the number of goals in the environment. Right? The log of the number of goals is basically the minimal set of bases that can represent all of the tasks in the environment. So that is why it is log goals. And of course, if you have n goals, then maximally you just need to know how to reach those n goals to be able to solve any logical combination over them. So that is the upper bound. So as t turns to infinity, the number of skills that the agent learns using the sub-goal approach is bounded by that. And note that the number of tasks in the environment is 2 to the number of goals, because the goals are either desirable or not for each task. So that is one result with respect to lifelong generalization. The other result in terms of the quality of the skills that have been estimated by the agent is that if the new task is indeed representable in terms of the task the agent has learned, then the inferred binary representation for the new task is going to be exactly the binary representation of that new task. Right? So T sub, the inferred one, is going to be exactly the same as the true T. And if that is the case, then the agent so this is going to be 0. So the agent will actually recover exactly the scale for the current task. All right. So this is in the case where maybe you're doing functional approximation and your scales are epsilon optimal. So after composition, you still have epsilon optimal 0 short scales. In the case where the new task is not representable in terms of the past task, then the suboptimality increases by the difference between the maximum and minimum reward in the environment. Cool. So that kind of gives us guarantees over the transfer of scales and the lifelong generalizability of the agent. So finally, how am I doing on time? Okay, cool. So I'm done about right now, though I think I should have finished earlier for questions. So let's take this domain where we have 40 goals. So each of these green squares here represent goals in the environment or potential goals in the environment. This red square represents the agent. So there are 40 goals in total, which makes about 1 trillion possible tasks. Now we are going to define 3 distributions over tasks in this environment. One is going to be the best distribution, which basically means that starting from task 0, the agent is going to only get the basis set of tasks. Right? So the first task is going to be a basis task, the second task is going to be a basis task, and so on. And so if the agent gets the best distribution of tasks, which is basically the basis set of tasks, then after only a few tasks, so about 6 in this domain, the agent is able to generalize over the full distribution using this approach. If the agent gets the worst case distribution, where each task is basically a goal that the agent hasn't seen in the previous tasks, then that worst case distribution, the agent is going to kind of like learn 40 tasks because there's 40 goals. And then from that point on, it's going to generalize to the full distribution. But then if we kind of use any of that transfer learning method that doesn't explicitly kind of like try to restrict the number of scales that are being learned and stored in the library of scales, and instead kind of like it just focus on faster learning or sample efficiency, but really still needs to store every single skill it has learned, then it just keeps on having to learn every single new skill and having to store all of those policies in its library of skills. All right, so MassQ is such an example. It was done by David Abel a couple of years ago, and it was kind of pretty much shown to be, or he pretty much showed that it was like the best thing you can do in terms of transfer learning, given a set of pre-trained skills if you don't use task decomposition or composition. If you kind of look at the number of time steps to convergence, so the worst case distribution looks like this. So as the agent sees every new task, it has to like learn it, but then once it sees the 40th task, it's able to generalize to the full distribution. So 0 time step or nearly 0 time steps needed to converge. For the worst case distribution, so that's the worst case distribution. For the best case distribution is this blue line here. After learning only 6 tasks, it has pretty much converged and is able to solve any new task in the distribution without further learning. MaxQ here kind of like is really good, right? Like for the first task, it takes a while to learn, but as the number of tasks increases, it gets better sample efficiency. But it still needs to learn these new tasks and it still needs to store them in its library of skills. So we don't want that. And if the distribution is like randomly sampled, so if each new task is randomly sampled from the set of tasks, then we see that our approach is again still able to very quickly generalize to the full distribution. Remember that there's about 1 trillion tasks here, and just after say like about 15 tasks, it just has generalized to the full distribution. Right. Cool, so that's pretty much the results. And so the kind of like takeaway here is that we can kind of leverage logical composition to achieve fast transfer between tasks. This kind of leads to very quick generalization. We can kind of put some bounds on the number of tasks that needs to be learned throughout an agent's lifetime. And this leads to both interpretable and sample efficient lifelong array. Of course, one restriction here is that we focus ourselves. That's where to goal-reaching tasks where goals are either desirable or not. So for such tasks, this approach is sufficient, but of course you can have tasks where maybe new tasks are other compositions of our previous tasks, not just logically decomposable, right? It could be like some nonlinear functions. It could be that maybe the states of the new tasks are not have like are not like the same as prior tasks, and there should be generalization with respect to that and so on. So definitely a whole lot more that needs to be done in terms of generalization, and a whole lot more that other people focus on in terms of generalization. But at least I hope this kind of like shows that this idea of kind of like giving new tasks, of trying to identify if they are expressible in terms of past tasks, and then be able to actually leverage that knowledge to generalize, is at least one way that we can improve generalization in reinforcement learning. So that's pretty much it. And thanks for listening. I'll take any question.